Hi everyone.
Hi.
Hi, how are you keeping, guys?
Yeah, not bad, Chen. How are you?
Good, good. So I want to start today. The forum was really quiet. It's normally not that quiet at that unit, and I'm a little bit concerned. Okay, so what we're gonna do in the first 5 minutes, I just want to go one by one and just tell me how do you get on. Did you manage to go through the material? Is there anything in particular you wanted to cover today within what we're supposed to be covering? Is there anything you want me to focus on? And then we'll take it from there. Is that okay?
Sure.
It's okay.
Excellent. Dermot, do you want to start?
Sure, yeah.
I got a lovely question from you, by the way, and we're gonna talk about it later, but just in general.
Yeah, I'm going to tell you now, I got to the section C, but I didn't get to section D. Had a bad weekend. So I'm going to have to catch up this week. Yeah.
Perfect. We're going to fully cover section D today, but okay. It might be kind of hard to grasp if you haven't gone through it yourself.
Mm-hmm. Okay.
But anyway, you can get back to me with more questions throughout the week. It's absolutely
sure.
Excellent. Thank you, Dermot. And Anne-Marie?
Yeah.
Hi.
Hi. I'm getting on fine. I am struggling, I have to say, with the immune system.
Yeah,
I can't really tell you what I'm struggling with. I'm just finding it a bit overwhelming. There's a lot in it. I don't. I've never come across a lot of the terminology before, so the lymphatic system and the skeletal system, that they're fine.
Yeah,
I'm comfortable with those bits. I've gone through all the material, so I probably just have to go through it again, and I've watched the videos, so I find that they're helpful. Yeah.
Excellent. So yeah, it's probably the toughest unit from all the physiology units. It's probably the hardest one. Yeah. It does get easier. It's very scientific. It's very, very detailed, which in the long run, it's going to really benefit you. I know that now it's really, really hard, and you might even have to go back. So when you're going to be doing immune imbalances, you probably go back, review what we've done, and it's probably going to make more sense. Because when we talk about the immune system in balance, so when it's supposed to be working the way it should be working, it's a little bit more hard to understand. I think it's easier to understand the immune system at an imbalanced state. I don't know if it makes sense, but when you understand the imbalance, it helps you understand the balance as well in some way. So I'm going to bring in a little bit of imbalances today just to kind of support understanding, but I'm sure you're not the only one, Anne-Marie.
Yeah, no, I'm not.
So you keep it all secret, it's all in your WhatsApp group, yeah? Okay, Camille, how are you getting on?
Hi, do you hear me?
Sorry?
Do you hear me?
Perfect, yeah.
Okay, yes, I went through all the material. As all the rest, I'm struggling with some parts, others are better.
Is there anything in particular you kind of find it challenging that we can cover today?
No, not anything in particular. There are some sentences I have to read 3 times before I really understand them. And overall, I understand it, but there are some parts that are more difficult to understand.
All right. So thank you, Camille. So what I'm going to do, I'm going to kind of tell you exactly what you are expected to remember, what you don't expect to remember, and what are the kind of more important aspects to focus on as well. So we're going to kind of talk about that a little bit today as we go through the slides. And let's see, Katie.
Okay, perfect.
Thanks, Camille. And how are you, Katie?
Hi, can you hear me?
Perfect, yeah.
Yeah, I'm the same. The musculoskeletal and lymphatic is okay, but there's nothing in particular in the immune system, but it's just in general. It's just there's just so much information that you find yourself having to read over and over and over. But the videos I found really helpful as well. So
excellent. Thank you, Katie. And Laura, how are you?
Hi, can you hear me?
Perfect. Yeah.
Yeah. So I kind of got a chance to go through all the material. But I found, like, in some cases I kind of thought, oh yeah, now I have it in my head, and then I'd see it presented in, like, for instance, the completed fact sheets a little bit differently, and then it kind of confused me, maybe the process of how things work. I found kind of, you know, it presented in different ways throughout.
Yes, you're right about that. And it's still today when I read different scientific papers on the same subject, and it doesn't have to be about the immune system, it can be about anything else. This week I was reading a lot about the mechanism behind obesity as an endocrine organ, and every scientific paper will talk about it in slightly more details, and they're not all wrong, they're all right, but it's just because it's such a fine level of anatomical and physiological details. I completely understand you. But again, today I'm going to kind of emphasize what is more important and what is the bigger picture as opposed to the little details. So what are we expecting from you to kind of take home from all those little details? I hope that's going to help anyway.
Yeah, it's just I probably would love if it was like all consolidated in order of the process rather than you get some detail here and then way more detail. It just kind of confused me. I think it threw me a little bit.
I think all you're expected to know is what's on the slide. So the slide will give you everything, even in terms of the assessment. Okay. But I know what you mean.
Yeah, I like the videos as well. I thought they were very good.
Exactly, yeah. Sometimes you need this the extra visual stimulation to actually understand how things work.
Yeah. And then the article, there was one of the articles on the kind of summarizing the.
Oh yeah, it's excellent actually. And I'm going to share with you a couple more articles tomorrow, but we'll wait anyway after today. Linda, how are you?
Hi, I'm well, thank you.
Excellent.
I managed to go through all the material. Yeah. Like others, yeah, it's very challenging. But I found the flow charts, the summary. Per pound, the audio, very helpful.
Excellent.
So when I went through the summary, yeah, so I was a little bit confused. So I had to go back to the major histocompatibility complexes and toll-like receptors and the not-like receptors, and just get it all, and then all the cytokines and get it all. Yeah. So. But yeah, I think I like it, and I find it very interesting. So
okay, that's good. That's good. Yeah. Thank you, Linda. And I think Martina, are you next? Yeah. How are you, Martina?
Hi. I find it very interesting. I find it also quite complex.
Yeah.
Like I have to revisit quite a lot the presentations. I mean, the videos I think are quite helpful. But it's just like the amount of information I find quite challenging at the moment.
Is there anything you want me to focus on today, guys? Like, is there anything in particular? Okay.
I think it's just, is it like, will we be repeating this stuff throughout the course? Because I think it's just the first time we're seeing all this new material. It's kind of hard to
absorb. A lot of new terminology. It's really, really hard. Yes, you will be repeating that. So what's going to happen this year is that in Unit 7, you're going to look at immune imbalances. And a lot of what we talk in this unit you'll revise it, but you'll also look at a lot of the concepts we talked about today and throughout the unit in the context of imbalances. So today we're going to talk about, for example, oral tolerance. But when you cover immune imbalances, you're going to look more closely at what happens when you kind of get to a state of loss of tolerance and autoimmunity. So you're going to need this basic understanding. But if you don't get it all now, it's absolutely fine, because you revise it when you need it. And it's going to make a lot more sense then. There's a lot of things in that PowerPoint that they're very detailed, but you don't really need to know them to the level that they are discussed in there in order to be like really good nutritional therapists, for example. But it is good to understand them for the sake of reading scientific paper, reading literature, listening to even really good bloggers or researchers. You kind of need to know some of the terminology or most of the terminology, but you're not expected to understand every little process. But again, I'm going to highlight that as well throughout the presentation today. So I hope that's going to help. Is that okay? I think Norma, you're next. How are you?
Hi, can you
hear you perfect? Yeah. Hello, Norma. Now you're muted.
No, sorry. Yeah, there's an awful lot to take on board. It's just the terminology. You've just got your head around one thing and then you're moving on to another, and it's an awful lot to take on board. I'm enjoying it, but my brain is fried.
I know.
No, my brain is fried. I'm
I completely understand you. It's normal. I would have been worried if you found it easy. Okay, so it's fine.
Okay.
A little bit. What I was worried about is that the forum was really quiet this week, and I knew it's really challenging material, and I was thinking to myself, what is going on? But it's fine. So I found out everything today, so it's okay. We still have another full week to ask me questions, and I'm happy to answer anything.
Okay. I think I wouldn't know where to start. It's such a deep hole. I'm just making my way around it.
Okay, so hopefully I can give
fascinating.
you kind of a more clearer view of what's kind of expected.
Brilliant. Yeah.
Excellent.
Brilliant.
So Patricia, how are you?
Good evening.
Hi. So I got a good question for you again. So I kind of have a general understanding of what you want me to revise, which we are going to.
Yes, definitely what I asked on my email, and I just wanted to clarify something. You were saying that the forum was very quiet this week, and from my perspective, I will have been asking a question a minute. It's
but
just a question. As soon as, like, for example, if I read something, if I'm allowed to give an example, I'm reading about the PRRs. And how they link to the dumps and maps, and I go, okay, then I get to a point, like few slides maybe towards the end, and I realize, do you know what? Actually, I might be wrong. Actually, how do you call them? Sorry, I lost the train of thought there. The different MHC1, class 1 and class 2, they're actually PRRs.
No, they're not. They're not exactly the same thing. No. So what happened is that the pattern recognition receptor, that's the first thing that allow the macrophage or the dendritic cell on the neutrophil to engulf pathogens, okay? Once it's been engulfed, it's been digested, okay? It's been digested, and just a fragment of it, of the antigen, is then presented, and it's then presented by the MCH complex.
But you see, I was looking online, and I found like information online that was saying they were PRRs, and I was like, okay, so this type of thing is what confuses me, and you know, you keep going forward and then you go backwards.
Well, generally speaking, you can ask me a question a minute on the forum. That's my job, and I'm happy to do that.
Okay.
But it's a good question. It's not really the same thing.
Okay.
Okay.
So that's what I thought at the beginning, and then as I went in, I was like, okay, did say it is actually. So
no. So PRR, it's like toll-like receptors and node-like receptors are receptors on the cell of on the cell of an immune cells. They're there in order to sense when there's a pump and dump. So when there's like bacteria, viruses, anything like that, it can be any type of cell. They'll just trigger it, but the MCH, so the HC, the molecular histocompatibility complex, and we're going to look at it now. They're actually a complex that's inserted on top of the cell after the antigen has been processed, okay?
Yeah.
Been processed, and it's been just a fragment of it is actually presented.
I'm totally, that's the impression I got at the beginning, and then last night I was reading the Essential Reading article, and from some paragraph in there I got that, and I was like, oh my god.
Okay, so I'm gonna have to read more about that, because I don't think I'm giving you wrong information, but I'm gonna have to read more.
No, it's just the Essential Reading. I'm gonna have to reread it myself, because I don't know where I got that impression from, to be honest.
Okay,
can I tell you
from that?
Sorry?
Anything else apart from that?
Yeah, there was just to clarify again, because my head, as other people have said, is fried. So page 105 of obviously the immune system one, they said a helper T cell produces cytokines that can cause the activity.
Sorry, can I stop you there? Because what I'm going to do, I'm going to go through those slides, and I'm going to ask you to stop me when you have questions, okay?
Okay, brilliant.
It's probably better if we do it in the context of the presentation.
Yes.
So that's excellent. Philip, do you have a microphone today? Can you hear us?
Hi, can you hear me?
Yeah, perfect. How are you?
I'm good, thanks. Hello.
Great.
Yeah, so to be honest, this is probably the hardest unit for me so far, next to the, what was it, unit 2 at the very start.
Yeah.
So it's just a matter, I guess, of constantly repeating everything, as everyone's probably saying. But yeah, I'll get there. It's slowly soaking in, at least.
Yeah, excellent. And Raquel, how are you?
Hello?
Hi.
Hi. No, I'm the same as the others. I think it's, can you hear me?
Perfectly, yeah.
I think it's really interesting, and I don't have a problem with the skeletal system or the lymphatic one, just with the immune system. Okay. It's not a problem, it's just there's a lot of information and sometimes it's quite confusing. And I did this morning the quiz, and Jesus, I thought I didn't know anything. I couldn't remember anything. So yeah, I did that everything at the second time, but the first time when I saw the question was like, I have no idea. I don't know.
It's fine, but that's why you have 5 times to do it, so it kind of gives you general understanding of what you need to focus on as well.
Yeah, no, it's really good and really focus on what you really need to know. But I hope, well, anyway, there's the same as the others. This web really helps just to have a better idea of everything. But for the rest, I think it's really good and very interesting. So.
And Ulrika, you're the last. Thank you so much. Sorry, Raquel. Ulrika, you're the last one. How are you getting on?
Yeah, I don't have much to add. I suppose it's kind of the same as everyone has said. The immune system is kind of complex, but very interesting. And I definitely felt like kind of looking at some of the stuff on YouTube, and I know it's kind of simplified, but then it seems to click a little bit more than what you read. So I think kind of go back over it again.
Yeah.
If I have time to look at the YouTube and then maybe try to read it again would help.
Okay, that's excellent. So what I'm going to do now, I'm going to start with delivering parts of the adaptive immune system. What I would ask you to do, if you don't have any background noise, you can unmute yourself because I'm going to ask you questions throughout. And what else I'm going to expect, and I'm expecting you to ask me questions as well in places you are kind of get stuck. So don't be afraid to unmute yourself, unless you have loads of background noise. It'll be great because I'm going to throw a question at you kind of throughout the part. The second part, I'm going to deliver mucosal immunity, which is kind of an oral tolerance. So this is kind of the part that our students normally struggling with. I'm going to focus on what you need to know for the assessment. And at the very end, we're going to look at the assessment questions, and you get a chance to ask me a question if you're not clear with anything. So I'm going to just share my screen now. Also, just letting you know that when I'm sharing my screen, I find it really hard to see the chat. So don't bother to send questions on the chat. You can just you can interfere me anytime because it actually doesn't interfere me if you're going to stop me in the middle for questions, okay? Can everybody see my screen?
Yep.
Excellent. So the adaptive immunity. So we know from last week we covered the innate immunity. Today we're going to cover acquired immunity or adaptive immunity. So just kind of very brief revision on the innate immunity. The innate immunity presents before any exposure to any pathogens. We are born with it. It's not specific. And it's very kind of basic and primal, yet very important. What we're going to find out today is the innate immune system, particularly some of the cells such as macrophages and dendritic cells are working closely and in really important synergy with the adaptive immune system. So the adaptive immune system, we know that as well, develops only after the exposure to inducing agents, such as microtoxins or other foreign substances. It involves a very specific response tailored to the pathogens. So it's really tailored to the type of the pathogen, what it is. Is it a cancer cell? Is it a virus? Is it a bacterial cell? Is it an intracellular or is it extracellular? Every different pathogen will provoke a different response. So just to very quickly sorry. Okay, so just to quickly revise what we've done last week, and this is one slide of the summary slides that I've shared with you, and I will encourage everybody to actually look at them. They're recorded as well, so I've done kind of a quick recording for those slides, but it's just to give you a very kind of quick summary of what it's covered. So we know that the innate immune system is kind of formed from the first line of defense, which includes the skin, the cilia, the mucus, the gastric juice in the stomach, different secretions, so perspiration, vaginal secretion, salivary secretion as well, and lysozymes, which are enzymes that are able to break down different pathogens as well. If the pathogen, whatever it is, bacteria, virus, or anything like this, manage to penetrate the first line of defense, then it'll reach to the second line of defense. The second line of defense, which is kind of slightly more, let's call it sophisticated, it's form of iron-binding protein. If you remember, those are the proteins that suffocate, to cut the oxygen supply from viruses or bacteria. Then we've got the interferons that are mostly interfere with viruses. We've got the phagocyte cells, so these are very important cells. They are the macrophages, the dendritic cells, and the neutrophils, and we're going to look at them a lot today. Then we've got the complement system, which is a system of 20 different proteins that work. It has 4 main kind of stages. So opsonization, which making the antigen more edible. Chemotaxic, which movement of, it's kind of the recruitment or the stimulation of movement of immune cells into the affected area. Then we've got inflammation and apoptosis or cell lysis. Then we've got antimicrobial protein, and finally we have inflammation, and we talked a lot about inflammation yesterday. I know I said it last week in terms of what you need to remember. You do need to remember the different stages of inflammation and the different characteristics of inflammation. All the rest you just need to know briefly what they are and what do they do, and of course you need to know that they are part of the innate immune system. Any other questions before we move to the adaptive immune system?
No questions.
Perfect, excellent. So the adaptive immune system, and what we're going to do now, we're going to look firstly at the cells of the adaptive immune system. We're going to look at the process of antigen presenting, which is really important. It's an integral and probably the most important part of the specific immune system or the adaptive immune system. And then we're going to look quickly at the process of cell-mediated and antibody-mediated. So I think the 3 most kind of important or main function or main characteristics of the adaptive immune system is, 1, specific recognition. So just as we said before, they recognize specific antigens, and therefore the reaction will be completely specific and tailored to the antigen as well. It develops over time. So our immune system, when we're born, is completely different to our immune system at the age of 3 years old, for example. And I didn't just say 3 years old because it's quite a critical window for immune development. And the adaptive immunity develops memory, and this is really important as well. And what the memory does is that the second and the third time we're going to meet the antigen, our body will be able to attack it and get rid of it a lot quicker than the first time. So cells of the immune system, anyone? They are the T cells and the B cells, right?
Yeah.
Great. B cells are matured in the bone marrow. And T cells are matured
in the thymus.
So when they leave the thymus gland, they are immunocompetent, means that they are ready to fight, okay? However, they are not fully differentiated. And when I say fully differentiated, it means that, yes, they are ready to fight. They do not know which unit they're going to be fighting at. I hope
Sorry to interrupt. There's a lot of background noise, and I actually can't hear you speak at all.
I can't hear either.
Yeah, someone has background noise, and you need to mute yourself. I don't know who it is. Yeah,
they're all muted because there's definitely we can't hear you.
Okay. Yeah. Okay. It's fine. If you cannot hear me, okay, that's fair. Is it okay now?
Yeah, it's good. Huh?
So immunocompetence, just as I say, means that B cells and T cells insert several distinctive proteins, which cause antigen receptors, into the plasma membrane, so that they can recognize and bind to non-self foreign antigen and distinguish between self and non-self antigens. What happens if a B cell or a T cell by mistake bind to a self antigen? What's this process called? What can this trigger?
Autoimmunity.
Exactly, yeah, exactly. And this is one of the main and important things of the B cells and the T cells, is to avoid avoid binding and triggering immune response to self antigens or to antigens that are part of our own body, and only attack non-self antigens. Is that all clear, guys?
Mm-hmm.
Perfect. So this diagram, we're just going to look at it quickly. So you can see this cell, this is an immune cell, okay? Something penetrates these cells, and it's a viral, it's a virus, it's an antigen. This antigen has been digested here, and a fragment of this antigen, it's been presented here on the surface of it. That complex called MHC complex. Now this is MHC1, we're going to look at it in a minute, but there's two different types of them. There's MHC1 and MHC2. This here, that receptor here, can only bind to one type of cell. It's very specific. In this case, it binds to a cytotoxic T cell, and the cytotoxic T cell will then will kill the cell. It will be basically either by cell lysis or by apoptosis, will kill the cell and also at the same time form memory cells. But this is, we don't need to go there just yet. So what we want to take home, or the message we want to understand from that slide, is that a viral, or it can be a bacteria, it can be any type of pathogen, invaded the cell. In the cell, or this is an immune cell, it will be digested, and a fragment of this antigen will be presented in a part of the complex that's called an MHC complex. This complex is very specific, and it can bind only to a specific receptor on a T cell. Is that okay?
Fine.
Do I need to repeat that, or?
Clear.
Okay, perfect. So, cells of the adaptive immune system. We know that we have T cells and B cells. Now, we've got three different types of T cells. Anyone? The first one is on the screen. So we've got helper T cells. Anyone remembers what are the other two types of T cells?
Cytotoxic and Treg.
Yeah.
Treg and T helper.
Excellent. So this is something that you absolutely have to remember. So we've got helper T cells, which are really important. We've got cytotoxic T cells, and we've got regulatory T cells. Now, the helper T cells, which are probably the most important for the adaptive immune system, they actually don't really kill any other cells. They are just as the name suggests, they're helping other cells, okay? And the helper T cells can themselves be redivided. So they can be redivided there to T helper cells 0, these are naive T cells, so they're actually not ready to be, they're immunocompetent, but they're actually not differentiated into any active T cell, okay? Then we've got T helper cell 1, we've got T helper cell 2, we've got T helper cell 17. We have more of them. This is just these are just the main ones. There's TH3 as well, and there's plenty of other ones. How does a helper T cells, how a naive T cell can get differentiated into TH1, TH2, and TH17? This is a really good question, okay? And this is really depending on the type of antigen and where it's originated from, okay? So what you need to remember is that helper T cells are a key player in the adaptive immune system. They don't actually take part in the killing itself, but what they do, they help. They send messages, so they can activate the cytotoxic T cells, and they can activate B cells as well.
Is the naive one the same as the T helper 0?
Yeah, that's the same thing. Yeah, it's the same name. TH0, it's naive T cells.
Okay, cool.
Okay, so in order to actually be helpful, the T helper, the naive T cells, has to get differentiated. So they get differentiated added to Th1, Th2, Th17. There's other ones that you don't need to know, but these are the main ones. Is that okay?
Mm-hmm.
And how do they get differentiated? Really, it's depending on the type of antigen they're being exposed to.
So are they in effect almost like in reserve, and then if an antigen is present, they get
They multiply then. So they basically, once there is a reaction, there'll be a very rapid proliferation of those T cells, of those helper T cells. Some of them will be actually kept as, or will be developed into a memory T cells. Some of them into whatever, depending on the type of the pathogen. We're going to look at it now. So if it's an intracellular pathogen, there'll be a very rapid and significant proliferation of Th1 cells. Okay. And if it's a parasite or an extracellular pathogen, so pathogen that it's not in the cell, but it's kind of more in the interstitial tissue, then it's the T cell will be differentiated into Th2 cell, and then this Th2 cell will stimulate antibodies production, okay?
Mm-hmm.
Th1 cell actually will stimulate cytotoxic T cells to then, so that will increase the expression of cytotoxic T cells. We're going to look at it in a diagram, which is going to make a lot more sense, I think, in a minute. But what you need to remember from that slide, and I think we've got a nice diagram. Yeah, so what you need to remember here is that T cells are matured in the thymus. They exit the thymus when they are immunocompetent, okay? They're still naive though when they exit the thymus. So yeah, they're ready to fight, but they haven't been located into a specialized unit now yet. They will, as soon as they meet a particular pathogen or an antigen, okay? So what you need to remember here is that a naive T cell will get differentiated into Th1 cell in cases of intracellular pathogens, okay? So you need to remember that. Th2 cells will get activated or differentiated in cases of extracellular parasites, so in pathogens that are originated not from inside the cell, but from outside the cell, in the body fluids or in the interstitial tissue. Th17 activates, it's a very important player in anti-inflammation and autoimmunity as well. And Th17 is very much linked to mucosal damage. So what kind of a mucosal damage will we see a lot in our clients? Think about it.
Leaky gut? Or?
Absolutely, yeah. So we can almost assume that people with leaky gut present with high level of Th17, okay? Th17 are actually very harmful to any mucosal membranes, in particular the epithelial layer. And what we didn't talk about it yet is T regulatory cells, and T regulatory cells will then stop the inflammation. They modulate the immune response. They make sure that once the immune response has been taken place, it can actually stop and shut down. If we've got chronic inflammation, so if the pathogen is being presented and it doesn't go away, it's persistent, T regulatory cells won't manage to do their job as effectively as they should do. Any questions so far? Excellent. So what you need to remember, T helper cells mature in the thymus. When they're immunocompetent, exit the thymus. There are three major types of TH or T helper cells that you need to remember, which are Th1, Th2, Th17, and then we also got T regulatory cells. So we said the T helper cells is only one type of T cells. The other two types of T cells are cytotoxic T cells and regulatory T cells that we actually looked at before, but it's not a helper T cell, it's a different type of T cell. So a cytotoxic T cell, it's different than the helper T cells. Remember we said the helper T cell, it doesn't actually involve in killing pathogens, it's just there to send messages and to help the overall immune system. cytotoxic T cells actually there to kill, okay? And it's also called CD8 because there's a protein on its membrane called CD8. You don't really need to remember that. You just need to remember what is the cytotoxic T cells, and that is called CD8. And cytotoxic T cells is normally get stimulated or active again, infected with intracellular pathogens and against tumor cells. So this is when it gets activated. Cytotoxic T cells can get activated by helper T cells, but it can also get activated autonomously under if there's tumor cells or infected intracellular pathogens. Okay, so I know it's a little bit confusing. We're going to look at it in a diagram in a second. Hopefully, it'll make more sense. And then the last type of T cell is a regulatory T cell, and we just talked about it a second ago. It modulates helper T cell activity. It's induced tolerance to antigens. We're going to look at that later as well, and keeping the adaptive immune system in check. Without regulatory T cells, inflammation will never stop. And you remember what happened in inflammation? There's a lot of mess of immune cells and a lot of active cells and a lot of oxidative damage as well. Is that okay?
Mm-hmm.
So let's just repeat that. What type of T cells do we have? We have three main types of T cells. What are they?
Helper, cytotoxic, and regulatory.
Excellent. And helper T cells, what can they get divided into?
0, 1, 2, and 17.
0, 1, 2, and 17. Excellent. Th1 will be mostly stimulated under what type of pathogens?
Intracellular.
Excellent. Yeah, perfect. And Th2?
Extracellular.
Could your bookshelf get into bed now? I have to be on the
extracellular.
So Th2, yeah, extracellular.
Answer questions when I put my earphones on, and then I'll like to be able to talk.
Sorry.
Get inside.
Does anyone have a question?
No.
Okay. And so Th2 is an extracellular. Do you remember how does Th2? What does it activate? It activates antibodies, okay? And what do we know about Th17?
It's important in the inflammatory response.
Absolutely, absolutely. So, so these are the T cells, and again, they're extremely important for the adaptive immune system. And what we've just covered now is the essence of what you need to remember so far. Okay, we're gonna get more complicated. I've got some background notes. So someone, I don't know who it is. Yeah, sounds good now. Now, this is, I'm sure that this is what a lot of you find a bit confusing. These are the major histocompatibility complexes, okay? And this is a note that Jess put to you to just tell you that the reason why we are mentioning them, and we know that they are very confusing, is A, because they are very important in the process of antigen presenting. But also, when you get more into your studying, definitely next year when you'll be looking more at scientific paper, and when you go into practicing, and you'll definitely look at more scientific paper, and even in different conferences, and maybe listen to podcasts or anything like this. These are one of the things that will be mentioned. And it's good to know, and it's good to understand, even though if it's a little bit challenging, you're not expected to really know the ins and outs of what is a major histocompatibility process. You just need to know it as an overall thing. So really what it is, it's located on the plasma membrane of body cells, in immune cells particularly. It's a glycoprotein, and sometimes, and this is important, it's referred to HLA complex. It's kind of the older name, but sometimes you come across it in literature. So the normal function of the MHC complexes is to help the T cell to recognize that an antigen is foreign and it's not self. And there are two main different types of MHC complexes. There's type 1 and there's type 2. And the reason why we mention them here is because type 1 will bind to one type of T cell, which is a cytotoxic T cell, and the other type will bind, or an MHC2 will bind into helper T cells. That's all you need to remember, really. So they found almost on all cells, they mainly interact with cytotoxic T cells. This is the MHC1, sorry, I should have said it again. So class 1, found on most cells, except red blood cells. They mainly interact with cytotoxic or CD8 cells, and they act to present endogenous antigens, okay, this is important, that originate from the cytoplasm. So different self-protein, viral protein, different cancer cells, and virus that takes over the machinery of the cell, the DNA of the cell. So what you need to remember here from the class 1 MHC complexes is that it binds to cytotoxic T cells, and it presents endogenous antigen. Again, this is one of the things that's much easier to actually take in when you see a diagram, and we are going to see a diagram very shortly. Then the other one is a class 2 MHC complex or molecule, and that would be found on certain immune cells, such as macrophages, dendritic cells, B cells, and also antigen-presenting cells, so different ones like neutrophils. And all you need to remember here is that MHC class 2 will interact with helper T cell or CD4. And the other thing you need to remember here is that it presents exogenous antigens that originate from the extracellular environment, such as bacteria or anything else like that, okay? I think, okay, so the last couple of slides, they are extremely complicated until you see it on a diagram, and I'm going to show you the diagram shortly. So if you feel a little bit confused about it, that's fine. If you're still confused about it after we are looking into the diagram, then start asking me questions. So the process of antigen or antigen-presenting cells, sorry, these are another kind of key player in the adaptive immune system, as well as the innate immune system. We looked at them last week. So dendritic cells, macrophages, B cells, they're part of the adaptive immune system, not a part of the innate immune system, but they also are they also have antigen-presenting abilities. So what they do, we already just mentioned that, they phagocyte the antigen, they digest it to learn about what it is, break it down into fragments, and they'll take those fragments and they'll bind them with the MHC molecule. Then they insert it into their complex, to the plasma membrane. Excuse me. So we need to remember, so this is one thing we need to remember, endogenous antigen will associate with MHC1 and exogenous antigen will associate with MHC2. And the insertion of this complex to the plasma membrane is called antigen presentation. So they took the antigen in, those antigen-presenting cells, so the dendritic cells, the macrophage, the B cells. They took the antigen in, they assessed it, they learned it, they broke it down to fragments. They took one part of a fragment, mixed it with the MHC complex, and inserted it into the plasma membrane. Now, the question if the decision whether to mix it with an MHC1 or MHC2 really depending on the type of the antigen. And this process called antigen presentation, and this is a key for the stimulation of the adaptive immune system. I'm going to skip that slide unless you've got a question on it. And I think I'm going to skip that slide here as well because I want to show you the diagram. So antigen presenting cells, they initiate the first step in the development of the adaptive immunity. And the more T cell responds according with the nature of the invading pathogens. We just said that. What we need to remember here is that naive helper cells, CD4 cells, will bind to antigen with MHC complex 2 on an antigen presenting cells, and they are stimulated to become helper T cells, so Th1 or Th2, that go on and stimulate B cells and cytotoxic T cells, which deal with extracellular pathogens. This paragraph sounds really complicated. So does the next one. What you need to remember is naive CD4 cells bind to MHC2 complexes. This will then give kind of give them an order to differentiate to a particular TH cell, so Th1 or Th2, and Th1 and Th2 can then we said earlier that they won't kill the pathogen, but they'll know what to do with it. So they'll know whether to activate B cells or to activate cytotoxic T cells. Okay. However, naive CD8 cells, so cytotoxic T cells, which are naive, means that they are ready to fight, but they are not completely specialized. They bind into antigen MHC1 complex. And they are stimulated to become cytotoxic T cells, which will then directly kill the infected or malignant cell by apoptosis or cell lysis. What I'm going to do now is that I am going to show it to you here on the diagram. I think it makes a bit more sense. So we are here, okay? We are here on the cell-mediated immunity. Can everybody see that?
Mm-hmm.
Excellent. So we've got different types of pathogens. We'll start with the easy one. So cancer cells or infected cells or cells that have been taken over by a virus will then we'll take the information about this type of pathogens will be processed by the immune cell and be inserted into an MHC1 complex. This MHC1 complex will then activate cytotoxic T cells, okay? On the other hand, pumps and dumps, so pathogen-associated molecular patterns, whether the bacteria or anything from the outer environment, will be triggered through Toll-like receptor or Nod-like receptors and will be activated then by macrophages and dendritic cells. Those macrophages and dendritic cells will then take the antigen, they'll process it, they'll learn about it, and then they'll insert it, they'll mix it with the MHC2 complex, which will be trigger, which will be then bind to a T helper cell. This T helper cell here, it's not differentiated yet, but this binds, or when it meets the MHC2 complex, and it meets the specific antigen presented to it, then it can learn it gives instructions to what cells it needs to be differentiated to, okay? So the T helper cell can be differentiated into Th1, Th2, Th17, or Th regulatory cells, depending on what the information we got here in this through the MHC complex. What's going to happen next? We said the T helper cell doesn't kill the cell itself. It will then either activate cytotoxic T cell, and cytotoxic T cell will cause cell lysis or apoptosis, and it give rise to memory cells. At the same time, the T helper cells will also give rise to memory cells, and they'll increase replication. We also know that some of the T helper cells can actually activate, especially Th2, can activate antibodies, okay? I'm going to go back. Any questions so far? Okay. So let's go back into, sorry, not this diagram. So I'm going to just look at the same process again from just looking at a different diagram. So here we got, anyone knows what type of cell is that? Looks like
Dendrite.
Dendrite.
Dendrite or macrophage, actually, they kind of look the same, I think. But yeah, it could be dendritic cells. Yeah, but you're right. It's either or. So it's either or. And what happened here is that this cell was detecting pump or dump. Okay. This antigen was broken down, was processed. The macrophage learned about what type of pathogen it is, or it basically processed it. It took a fragment of it and it kind of inserted here to the MHC complex. Now, because it's not a cancer cell, or because it's not a viral cell or cell that comes in from within the cell itself or within the body itself, it's an extra kind of extra body antigen, so it could be a bacteria, let's say. Therefore, it is bound to an MHC2 complex, okay? This MHC2 complex then fits perfectly to the T helper cell receptor, okay? The T helper cell here, is that a naive T cell or is that a differentiated T cell?
Naive.
Naive, absolutely. This connection here gives it the information to know how to be differentiated to, or to what type of T cell he needs to be differentiated to. What happened next is that the T cells, it's cloned, so there's a very rapid and significant replication. And in this case, it's activating B cells, but it can also activate cytotoxic cells. So it's really depending on what type of antigen is kind of being presented. It can activate B. It can activate B cells if it's a parasite or endogenous type of antigen, or it can just stimulate cytotoxic T cells, which then will kill the cell by apoptosis or cell lysis. And then the other scenario is that the cell that is detected by our immune system is an infected cell or a cancer cell. A fragment of it will be then mixed and presented with the MHC complex 1, which will then bind to a cytotoxic T cell. And here the process is a lot quicker, but because the cytotoxic T cell, what it does, it just basically make a puncture in the cell, so it kind of stab the cell and lyse it, or it can cause to programmed cell death by apoptosis. In both scenarios, so it doesn't matter which the scenario is, in both scenarios there will be a very rapid and significant replication of the T cell or the cytotoxic T cells or the helper T cell, and memory cells will also be formed. Does that make any sense, or is it kind of still very vague? Anyone?
It's fine.
It's okay. Okay.
It's okay.
It makes sense. It's just always hard to remember. Yeah.
Yes. Now, remembering, it's a funny thing, okay? Because I know now it's not related to the immune system, what I'm going to say now, because when I teach different units in third year and generally in kind of that are not physiology, I always say to the student that understanding, it's the very most, or not understanding, excuse me, memorizing, it's probably the most inferior type of learning, because you're really kind of supposed to aim for understanding and then to critical evaluating and kind of different skills, different kind of more superior types of learning. But when it comes to such a basic physiology, I know it's not very basic, but when it comes to that kind of type level of physiology, it's really kind of hard to understand without memorizing it, I suppose. But what you kind of try to what I'm trying to say is that you should probably try to understand it rather than just memorizing it. And you won't really memorize everything, which is absolutely fine. And to be honest, this type of material is not something that it's really, I don't want to say really important, because it is important to know and understand, but it's not something that you'll be using in your clinic, in your clinical practice on a regular basis, for example. But you do need to know that for an overall understanding.
Can I interrupt for a sec, please?
Absolutely.
Sorry, it's Jill here. Just back on that diagram, the granzymes and the perforins, what exactly are they? I'm sorry, I haven't really studied it.
The perforins, they puncture the cells. So the perforin is like knives that stab the cells, okay? What happens when they stab the cells? A lot of liquid comes out. The granuzymes are enzymes, and those enzymes will actually cause, will digest it. Is that okay?
Yeah, kind of, yeah.
So they're chemicals, but basically
chemicals.
They are chemicals, and they take part in the kind of killing of the pathogen. And what they do is, so perforin will form pores in the cell. So basically, will stab the cell until all the liquid, all the juice of the cell comes out. I'm sorry, I'm kind of saying it in very basic terms, but probably easiest to understand.
That's good. I can understand it that way.
Yeah. And the granuzymes are just
enzymes.
Yeah, they're enzymes, and they digest it.
Okay, thank you.
Okay.
Sorry, I have a little question. Is that okay?
Absolutely, yeah.
Yeah. Sorry, I'm a bit confused because I've been reading in a few slides. There's another slide in page 105 that confuses me as well. It might be just semantics. But okay, so we've seen that we have that 3 types of cells: the CD4 T helper, the CD8. I thought it was already a cytotoxic.
Yes, it is cytotoxic.
And so it is already cytotoxic or becomes cytotoxic?
So it is cytotoxic.
Yeah.
When it comes out of the bone, when it comes out of the thymus.
Yeah.
It's already a cytotoxic T cell.
Okay.
But it's not. It's like fully, I don't know how to explain it. It's fully trained, but it's not experienced yet. You know what I mean?
Yeah, yeah,
yeah. It's trained, but it's not specialized.
Okay.
Okay?
Yeah, okay.
Okay.
Perfect, thank you.
Yeah. It's more like the helper T cells that are just helper T cells, but they are not differentiated into the different types of T cells. They are named. Okay?
Yeah, perfect. Thanks.
So, can you briefly explain the adaptive immune response and how it differs from the innate immune response? Let's see that. So, okay, I think we've covered that all. I think we can move on because otherwise we'll never get into the really interesting part 3D. So this diagram, again, this is kind of those kind of a chart. Like I think there's like 4 or 5 of them. And they can really support understanding. I've recorded them as well, but they can really support understanding together with the main material. So you just put everything, they take all the 150 slides and put them into like 4 different flowcharts. So I would kind of recommend you to kind of look at them, maybe print them. You may want to listen to the audio recording of them. You may not, which is fine as well. But I think all the details on those charts are kind of, those are the details that are mainly important to understand. So we're going to go very kind of briefly on the process of adaptive immunity, of cell-mediated and antibody-mediated immunity, because we kind of need to move on. So the adaptive immune system, we know there's B cells, there are T cells. The T cells there's 3 main different types of T cells. Those T cells, some of them can get differentiated into a more specialized one. And we also know that the T cells can activate B cells, and that some T cells can activate cytotoxic T cells. That's what we know so far, right? So the cell-mediated immunity, which is T-cell-led, is particularly effective against intracellular pathogens such as virus, bacteria, or fungi from within the cell, and also some cancer cells and foreign tissue transplants. And cytotoxic T cells directly attack the pathogenic cells, okay? So cytotoxic T cells, they're the killer cells. They're the one that kills. Helper T cells, they're the one that helps. And regulatory T cells are the one that stops the fight. Then the second type of adaptive immunity is antibody-mediated immunity, and it works mainly against extracellular pathogens, which include viruses, bacteria, fungi that are in body fluids outside the cells. So what you need to know here, what you need to remember here is that cell-mediated immunity is led by what type of cell? T cells, okay? And what you need to remember here is intracellular pathogens. And then B cells, it's antibody-led, antibody-mediated, and it mainly works against extracellular pathogens, means that they're not within the cells, but within the body fluids or in the interstitial tissue. So those B cells will then transform into plasma cells, which will then synthesize and secrete specific proteins called antibodies. So the B cells, themselves needs to kind of go a few steps before they can actually be effective in actually neutralizing or killing any other pathogens. They need to get to be antibodies, and in order to become antibodies, they need to be transformed into plasma cells, and these plasma cells are then will secrete or will create those antibodies. And a given antibody can bind to and inactivate a specific antigen. And since antibody-mediated immunity involves antibodies that bind to antigen in body humors or fluids, it is referred to as humoral immunity. And this is actually can help you really remember that antibody-mediated actually, it's mainly against virus or bacteria or other pathogens that are in body fluids, okay? That's kind of just like a little hint. So this is a really good diagram, and it kind of shows you the two different cell-mediated and humoral-mediated immunity and what's involved in them. And I think we kind of went through, we already kind of talked a little bit about it today. So first we're exposed to an antigen. And now it's depending really if it's really depending on the type of the antigen, right? We know that some of them will activate cytotoxic T cells and some of them will activate the helper T cells. Do you remember that? Do you remember what type of cell will stimulate or will bind to cytotoxic T cells? It's actually
MHC2.
Yeah, actually, MHC1. Hey.
Oh, 1.
Yeah.
Okay.
MHC1, but what type of antigens? Okay, say it on the screen.
Oh, endogenous.
Cells and cancer cells will activate cytotoxic T cells. What happened then? Very easy. Activated cytotoxic T cells will kill the cells. They're killers. They also form memory cytotoxic T cells. So this is the kind of easy scenario. If it's a cancer cell, if it's an infected kind of intracellular cell, will get activated by the MHC1 complexes to the cytotoxic T cells, and this is a very easy and straightforward scenario. Problem is, if it's a pump or a dump that's activating the helper T cells through MHC2 complex, what happened then? It's really depending on the type of the pathogen, okay? If these helper T cells get differentiated into Th1, what's most likely to happen is that it will secrete different cytokines that will activate cytotoxic T cells. And then those cytotoxic T cells, we already said, they're going to kill the cells and form memory cells. If these helper T cells get differentiated into Th2, it will then stimulate B cells. And we're going to look at the B cells mediator immunity in a minute. Either or, it'll give rise to active memory and helper T cells. So there'll be replication of more of those cells, and memory cells will also form. Is that okay? Does that make sense? Any questions on that? Okay. So we said it really depending on the pathogen. Cancer cells, infected cells will activate cytotoxic T cells. Different types of cells, such as bacteria or viruses originated from the kind of outside body, will be stimulating the helper T cells. Helper T cells will then differentiate, and it's depending on the helper T cells, it's differentiating into That's what will determine the next step. One fate is that it will stimulate cytotoxic T cells. The other fate is that it will stimulate B cells. Either or, memory T cells will be formed. I'm going to skip those slides unless you want me to cover them. Is that okay?
Mm-hmm.
Perfect. Let's look at what happened in the other side of the diagram, which is the antibody mediated immunity. So the helper T cells, most likely it's a Th2, and probably it's a parasite, as we already know. In that case, the helper T cells and the Th2 will secrete cytokines that will stimulate the secretion of B cells. B cells, they're still not useful unless they became antibodies, okay? So what happened next is those B cells going to get, they're going to give rise to plasma cells. Plasma cells are going to give rise to antibodies, and antibodies will then fight against the particular extracellular pathogen. Just like the T cells, B cells will also form memory cells, which are extremely important in terms of future immunity, or if we ever going to meet this type of pathogen again. Is that okay? Okay, so let's just kind of question you about this diagram. These helper T cells has differentiated into Th2 helper cell. What's the next step? What will it stimulate?
B cells.
B cells, right? And are those B cells active, or do they need to go through a few more steps before they become?
Yes, they're not active yet. They're still naive.
Well, they're active, but they're not. They're not killers, okay? They're yeah. And what will they give rise to?
To plasma cells?
Absolutely, and those plasma cells will give rise to
antibodies.
Antibodies. And those antibodies are those killer cells, or they can neutralize. They can do different things, but they are the main kind of combat soldiers of this B-type immunity. Either or, in any case, those helper T cells, cytotoxic T cells, or B cells, apart from having or apart from replicating themselves very rapidly, they will also produce memory cells. So quickly going through antibody-mediated immunity, and then we're going to move forward then, because we are not really on time. So as B cells mature during embryonic development, they develop surface receptors that allow them to recognize specific antigens. They will travel then to the bloodstream, distributing throughout the lymph nodes, spleen, and the tonsils. And then once they reach their kind of sites, they stay inactive, and they stay very sleepy and unresponsive unless something happens. And when something happens, they'll wake up very quickly. A lot of the B cells remain actually inactive for our entire life. But upon recognition or an encounter, so when something pokes them, then the B cell receptors will bind to an antigen, and then process begins. So B cells may also get activated, or they mainly get activated actually by the helper T cells, and helper T cells recognize, we already know that antigen MHC2 complex presented on the surface of the antigen presenting cells and produce interleukin-2 and interleukin-4. You don't need to remember that, okay? Just in case it's kind of like if it's kind of reduce your stress level, this is the part you don't need to remember. And these cytokines function as co-stimulator to activate B cells. All you need to remember is that process is led by different cytokines. If you remember interleukin-1 and interleukin-4, great. If not, it's absolutely fine. Once they're activated, B cells undergoes rapid proliferation, which means multiplication and differentiating, forming plasma cells and memory cells. So plasma cells are the effectors of the B cells. They secrete specific antibodies, which in turn circulate in the lymph and the blood and to reach the site of invasion. Memory cells, they are not killer cells, but they play an important role in future immunity to an antigen. So they just store all the information and go to sleep until the next encounter. And a few days after the exposure to an antigen, a plasma cell secretes hundreds of millions of antibodies each day for about 4 or 5 days until plasma cells dies. Any questions on this process?
No.
Excellent. So this is the complete diagram. And if you look at it at the beginning of the module, it looks very, very scary. I think that after today, if you look at it in the end of the week, I hope it's going to make sense to you, okay? So what we know about MHC2, it gets stimulated by, or it gets, MHC2 binds to pumps and dumps on macrophages or dendritic cells or different antigen-presenting cells. It gets then differentiated, it then binds to a specific T helper cell, and which then get differentiated into Th1, Th2, Th17, and it can give rise to Th regulatory cells then when the process is finished. Th1 can stimulate cytotoxic cells. Th2 will mainly stimulate B cells. B cells will then differentiate into plasma cells to antibodies, and we've got different types of antibodies, which I don't think we have time to cover today, unless you really want to. Plasma cells, cytotoxic T cells, and T helper cells will all form memory as well. Just a couple of other things. So I don't know if you remember last week, but we did mention that antibodies can actually activate the complement system. So this is one of the ways they are working. And I think that's it. Any questions here? Okay, so I don't think we have time to do anything else here because we're quite out of time. Let's just gonna go quickly on what cytokines are, because I don't want you to get too overwhelmed with them, because all we need to have is very basic understanding in this module, or this unit, sorry. So,
yeah. Sorry for interrupting.
No, no.
I think it is really complicated, and we seem. I'm just wondering why we're in such a hurry. Do you know what I mean? That we can't go a bit slower. It is a lot of detail.
In terms tonight, you mean, or in general?
I just mean for the whole subject. I just feel I have to say that at this point because, and maybe that's not right to say it, but
no, absolutely right to say it. And well. So basically, the history of the whole thing is that last year we only had 2 weeks to cover the immune system. Until now, with basically the last few years, Unit 5 and Unit 6 ran together, and we only had 2 weeks to cover the immune system, which was really, it was even, now you have almost 3 weeks, and you still feel overwhelmed. So we did increase it, and the idea, that's one of the reasons why we separated Unit 5 from Unit 6, and I think they've been kind of, Unit 6 has been kind of distributed between different units, but we know that it's really complicated, and we know that there's so much to it, and it's a shame that we don't have a lecture weekend this year, because it's those students who want to kind of go through the material more slowly and more directed. It is easier to do it when you can do it over the 2 days. But when I only have 2 hours to cover all that, I kind of have to prioritize as well. And what we're going to do next, which is mucosal immunity, it's not less complicated. And
okay.
It's very important.
Sorry, I don't mean to hold you up any more than...
No, absolutely, it's fine. And as I said last week, I'm happy to stay until 9:30 tonight. If you're happy, I don't want you to send you home early. If you feel, I'm going to say it now and I'm going to say tomorrow. If you feel you need another kind of a Q&A session towards the end of the week, let's say Thursday afternoon, Thursday evening, I'm more than happy to do that. I feel really bad and feeling that I'm letting you out of this unit when you're really overwhelmed. But unfortunately, this is what's been set up, and I cannot really change it too much. So all I can do is say, let's say another extra half an hour this evening. If you really want to do another Q&A session on a Thursday, let's say, I'm more than happy to do that. I can talk tomorrow.
Okay.
You're just going to need to let me know, okay?
Yeah, okay. Thank you.
Excellent. No problem. Yes.
Just a very quick one. We just skipped through the antibodies, and I know it's reiterating what we're talking about here, but will we go back to the antibodies at some point? Like, I do
if
think...
you want, I can go to, yeah, we haven't actually reached the part of the antibodies, so I can go through it as well if you want me to.
Yes, but I would like if everybody's happy with that. I don't know.
Yeah, absolutely, yeah, no problem at all.
Thank you.
So just to kind of look quickly at cytokines. So cytokines are extremely confusing, and that's a great first sentence. And new ones or new function of existing cytokines are continuously being discovered. And this is one of the reasons why it makes it really hard to learn, because the slides becomes very quickly out of date. So you need to kind of make sure that you keep on top of your resources yourself. All you're expected to know at this stage that the cytokines are they kind of help you, or they're sending messages. They're like the postmen of the immune system. And so what you need to be aware of is two phrases: immune stimulated and immune suppressing. And authors should make it clear which part of the immune system is being stimulated or suppressed, the innate or the adaptive, and so forth. What I really need you to take home for that is that we have strongly inflammatory cytokines, so cytokines that are strongly related to inflammation, or can cause inflammation. They send messages to induce inflammation. And we have cytokines that are anti-inflammatory, means that they will send messages to stop or reduce inflammation. What you also need to remember, and this is important because this is something that you see all the time, is that interleukin-1, interleukin-6, tumor necrosis factor alpha, and interleukin-17, these are the most inflammatory cytokines we have to date. That's what we know of to date. So this is something to remember, okay? These are the inflammatory cytokines. We have interleukin-12 and interferon gamma. They are kind of slightly inflammatory as well, not to the same degree. As far as we know now, they are less inflammatory than those ones. Interleukin-1, interleukin-6, TNF-alpha, and interleukin-17. A lot of times, so when you get into third year and when you're going to start practicing, you're going to look at different nutraceuticals and different supplements, and those different supplements, you may read about them that they can reduce the expression of interleukin-6 or interleukin-1. So, for example, curcumin or resveratrol, two very kind of powerful anti-inflammatory supplements or nutraceuticals. Both of them can inactivate the expression of interleukin-1 and interleukin-6, and therefore kind of help with to reduce inflammatory conditions. So this is why you need to know and remember those. What you also need to remember is that we also have some anti-inflammatory cytokines, and those cytokines are the ones that will be expressed in cases of anti-inflammation, or these are, as nutritional therapists, these are the ones that we kind of look to increase normally. And these are interleukin-10 and transforming growth factor beta. So this is what you kind of need to remember from cytokines to this level. You're going to talk a lot more about cytokines in Unit 7 when you talk about immune imbalances, but for the sake of Unit 5, all you need to know that you've got the main inflammatory cytokines are interleukin-1, 6, 17, and TNF-alpha. And the anti-inflammatory cytokines, those that will give messages to stop inflammation, will be interleukin-10 and transforming growth factor beta, TGF-beta. Is that okay?
Okay.
Yeah.
Excellent. Okay. There's more cytokines. I'm not going to go through them if that's okay. I think it's something that you can read after. I think those are the most important ones.
Yeah. Perfect.
So let's have a look at the immunoglobulins or the antibodies. So immunoglobulins, also known as antibodies, and these are really glycoproteins, and each antibody has two identical binding sites. Here they are. And these sites are referred to as variable regions because the order of amino acids in these regions can vary hugely, so the shape of the binding site can be altered to fit an antigen. And it's very important to recognize and to understand that each antibody binds to only one specific antigen. Remember, we've got so many different antibodies in the immune tissues, such as the spleen and the lymph nodes, and they're there, but they're asleep until they get poked and get activated, right? And then when they get activated, they're very fast to react. So what is important to remember is an antigen, there is a specific antibody that can bind only to it. It's absolutely fine because they get multiplied so quickly in times of infection that there's going to be plenty of them very quickly. So there are 5 different types of antibodies. There's IgG, IgA, IgE. So these are the 3 main antibodies we will talk about today. There's also IgM and IgD. So IgM and IgD are kind of amateur ones. They can actually get differentiated even further to IgG, IgA, or IgE. And IgG, IgA, and IgE are the ones that we read a lot about in literature, and as nutritional therapists, we deal with them a lot. And each class of antibody has a distinct chemical structure and different functions. So just as I said now, the IgD and IgM, both of them are, they're a little bit amateur, so they're not as specialized as the IgA, IgE, and IgG. Their function is mainly as an antigen receptors on B cells that have been that have not been exposed to antigens. It has been shown to activate basophils and mast cells to produce antimicrobial factors. And IgM are the first antibody class to be secreted by plasma cell after initial exposure to any antigen. IgMs are the antibodies that activates the complement system, and they cause sticking of cells together, basically, and cell lysis of microbes. But what happens is that then they get differentiated into IgG, IgA, and IgE. And those, sorry, now I'm going back. Those will have a defined role in the immune system. So you do need to know now IgA, IgE, and IgG, you do need to know their roles. IgA is a very important antibody that's found in mucosal areas. So anyone can think of where can we find a large, huge amount level of IgA? It's like to be, it likes to live inside mucous membranes. Where will we find a lot of them?
In the gut. In
the gut, yeah. We're going to look at it now in a minute. So IgA likes to live inside a mucus, and it'll be in areas such as the gut or the respiratory system as well. But we'll talk about it a lot today in the context of the gut. Then IgE, they are located on mast cells and basophils. When they bind to an antigen, they trigger histamine. And what histamine will then cause?
Vasodilatation.
Yeah. So that's the first step of
inflammation.
Yeah. Yep. What we need to know about IgE is that when they get stimulated, the reaction is super fast, okay? So if we are allergic to peanuts, this is an IgE-mediated response, okay? And there'll be a huge surge in histamine released, which will then give us those really severe characteristic of true inflammatory or true allergy, which is IgE-mediated allergy, okay? Then we've got IgG, and IgG has 4 different forms and provides the majority of antibody-based immunity against invading pathogens. It is the only antibodies capable of crossing the placenta to give passive immunity to the fetus, and it's the most prevalent and most common antibody in the blood. It can enhance phagocytosis, and it also, such as it's together with IgM, triggers the complement system. IgG can also get activated as a result of not a true allergy, as more of a sensitivity, But unlike IgE, it'll take him time to get activated. So let's say if you have sensitivity to gluten, okay, if you don't have a true allergy, if you've got only sensitivity to gluten, the symptoms may only appear a few days after, okay? Or sorry, not the symptoms, excuse me, but the IgG reaction may only appear a few days after. If it's a true allergy, such as peanut allergy, it'll be immediate. So the histamine will be triggered immediately upon detection. With IgG, the reaction will take place a bit later. And here is just explaining it again. So classic type 1 allergy is when the immune system produces specific IgE antibodies. And these antibodies lead to an immediate allergic reaction. The symptoms will appear within seconds or minutes, and anaphylactic is probably one of them. It's the most severe one of type 1 allergy. And type 3 sensitivity is when the immune system produces specific IgG antibodies, and these antibodies can lead to inflammatory processes. They'll be less pronounced and they'll be less easy to detect. And when it comes to food sensitivity, it's a lot harder to detect those kind of foods that we are maybe sensitive to, because the symptoms may appear up to 3 days after the exposure to the allergen. And this is more difficult to pinpoint, which is what triggering the response because of the delay. When you do a finger prick test to find, do you know those food intolerance tests?
Mm-hmm.
Those are targeting IgG antibodies, okay? If, for example, you ate, sometimes, you know, when you eat like a walnut, or for some people it can be like different types of fruits or something like this, you feel straight away the tingling in your tongue. Anyone knows this kind of feeling? Or kind of itching in the back of your throat? This is a true allergy. This is an IgE-mediated allergy. And most of the time we'll know what it is because we know that we've just eaten something, and we can kind of like, we can link it. If it's anaphylactic, obviously we'll know that we may be like allergic to peanuts or bee pollen or anything like that. But with the IgG response, so much harder to target, because we can eat wheat or gluten now, and we won't have the symptoms until 3 days later. And this is one of the reasons why food intolerance tests are trying to detect IgG antibodies. Again, this is quite a controversial test, but I'm absolutely not going to go to it. I'm not going to talk about it today. Any questions about antibodies so far?
I have. Could we tell that IgM are like memory cell, or
they're not really memory cells? Not exactly, because they will then differentiate into one of, yeah. But they're more like amateur. They're more like kind of like they're childish. Do you know what I mean?
Okay.
Yeah. The memory cells will be actually no, it's not really correct to say that they're memory cells. They're still childish. They're not completely mature. When they will be mature, they'll be coming to the IgE or the IgG or the IgA, which are the real kind of like, you know, when those ones have really defined and strong characteristics and personality. Does it make sense?
Yeah, that's fine.
Excellent. Perfect. So neutralization, if it's okay, I'm going to skip through it, but it's just one way where the way the antibodies can neutralize toxins. You can read through it later and get back to me with questions. Opsonization, do you remember what it is? We talked about it last week.
Is to make the pathogen more eatable? Or?
Yep, absolutely. So it's easier to be phagocytes.
Yeah.
It's activating the complement system as well. We know it already. And then there's a few slides about immune memory and artificial immunity, and they're all relatively straightforward. I'm not going to look at them again today. But what I would ask you and really encourage you to do is to get back to me on the forum and ask questions on the forum. And it can be a really small question that you may think is a little bit stupid, but it's never stupid. Most case scenario, if you have a question, someone else have the same question. And as I said before, if you feel like you need another Q&A session towards the end of the week, it's absolutely no problem. Let me know and post on the forum, send me an email, and I'll talk tomorrow, and hopefully we can arrange something for Thursday night, okay?
Thank you.
Excellent. So what we're going to look at now is for me, the icing of the cake of this unit. I absolutely love it. I think it's fascinating, and it's the integrative immunity, the role of the digestive system in immune homeostasis. It's also called mucosal immunity. It's known to be complicated. It's quite, it's not a recent type of research, but it's evolving and it's changing really fastly, and it's full of really interesting different mechanisms, and it's just kind of one way to show how amazing our body is in terms of protecting ourselves from different invaders. So this slide, you already covered the immune system, and not sorry, the digestive system at Unit 4. So you kind of know about the role of the role and the structure of the gastrointestinal mucosal membrane. It is very large. It's the largest surface or interface between our internal and external world. So the lumen, the little kind of tube, it's really the exterior, and what's inside. If you cross the lumen to the other side, then you get into the body. So this kind of mucosal, the whole collection, so this tube, whatever happens on each border of it, it's really interesting. There's a collection of loads of different types of cells, and we're going to look at them now. So as you already know, the main function of this membrane is to regulate absorption of nutrients, electrolytes, and water from the lumen into the circulation, which is called assimilation, and then to prevent the entry of pathogenic microorganisms into the circulation, while tolerating and benefiting from the existence of beneficial microorganisms. And lastly, to biotransform and eliminate toxins, and this is not something that we're going to talk about today. So there's all different types of cells on this, the mucosal barrier. We've got goblet cells. Anyone remember what goblet cells will produce? Anyone?
Secrete mucus.
Absolutely. So goblet cells secrete mucus. And what kind of likes to live inside the mucus? What type of antibodies?
Macrophages? No.
There's certain types of antibodies that likes to sit within the mucus and live there happily. And these are the
IgA.
Yeah. And then we've got Paneth cells, and Paneth cells will produce antimicrobials. We also have the enteroendocrine cells, and enteroendocrine cells will have loads of toll-like receptors and node-like receptors, so they'll also help with immunity regulation. And then we've got, of course, the absorptive enterocytes, which will contribute to the barrier function, but also to absorbing different nutrients and electrolytes and all that. So an enormous fraction of the immune system's function is to control our relationship with the microbiota. And we just said that at the epithelial barrier of the mucosal layer, there's IgA, there's dendritic cells, and then there's T cells, and all these make up the mucosal immune system that helps to limit the passage of antigen derived from food and microbiota into the gut-associated lymph tissue, and therefore preventing excessive activation of the immune system and maintaining immune homeostasis. Okay, let's kind of simplify it. In the lumen, in this tube, this huge movement of different components that our body may think are pathogenic, but they really aren't. They're completely friendly. So our microbiota and food components and different stuff like this. But every now and then there'll be a pathogen there that they need to fight. Think about the mucosal immunity like the security at an airport, okay? So when you go to an airport, there'll always be different stages of security along the way, right? And those stages of security taking place, there's huge amount of people. Most of them are friendly. Most of them are completely harmless. They still have to go through those levels of security. This level of security is so it's so specific and it's so well organized that they let the friendly people in, and they'll know exactly when to stop this person who might be a danger, right? Our mucosal immune system is exactly the same. So there's loads of different stations of kind of checkup points. Most of the passengers, most of the different components will be introduced to are completely friendly. So food particles, our microbiota, but every now and then there'll be a pathogen. And when there's a pathogen there, our immune system needs to know that this is dangerous and this needs to be arrested. Okay?
Okay.
I hope it helps. I know it's kind of a stupid example, but that's the only thing I could think of. So the mucosal system must economically select appropriate effector mechanisms and regulate their intensity to avoid bystander tissue damage. And this is an important slide. So the gastrointestinal barrier is composed of epithelial cell lining of the digestive tract. Remember, they're only one cell thickness, so they're very, very thin actually, and they are very, very fragile. The space between them is sealed by tight junction complexes, and those complexes are consisting of 50 types of protein. So the different cells of the epithelial layer, they need to be very closely intact. They're sealed, but they're not completely sealed. Those tight junctions, they can open and close when they're needed, but it needs to be highly regulated. If they're not highly regulated, and if they get a bit more, the permeability increased, and we get increased permeability and leaky gut. In healthy condition, those tight junction protein will keep the mucosal layer nice and intact. And this is regulated by zonulin, and I think I talked about zonulin in one of my forum posts. Zonulin is an important protein that, although in the relation to this unit you're not expected to remember, but what you need to remember is that zonulin is that type of protein that can control the opening and closing of the gut. It can get, so what is believed, now this is something you don't need to remember, but it's very interesting, and I had a question about it today. So what we need to know is that gluten might, we have some evidence to say that gluten might interfere with the function of zonulin. So instead of being very targeted in opening and closing those tight junction, you get all messy, and gut permeability may be increased. And this is why some people may suggest that gluten may not be good to take in high amounts to anyone, because it may interfere with zonulin, and if it interferes too much with zonulin, then it can interfere with those tight junction, and then it can lead to increased permeability. Is that okay?
Yeah.
Now, this hypothesis, which I just told you now, there are research to demonstrate it. It's not very strong hypothesis. It is there, and you should know about it, because that's what we do. But it's not something that it's, I cannot say proved, because nothing can really be proved, but it's not something that it's very strongly agreed. So it's just something that the research is there, but maybe it's not very strong research, but it is there.
And Chen, when you say permeability will be increased, that's leaky gut, right?
Exactly.
Yeah. Yeah,
so
okay.
Those tight junction, okay, so they're here, they're not, it's not right to say that they're completely sealed, because they're not, because they do let some particles in and out, but it'll be in a very controlled manner. So the increased permeability will lose this control, and things like bigger protein and things that are not supposed to diffuse through this tight junction will get diffused. Actually, it's very interesting. When a baby is born, its gut permeability is very loose. So it has an increased gut permeability. Babies are born with an increased gut permeability. And anyone can guess why?
Because it's sterile, maybe? I don't know.
Because just to allow kind of a quicker absorption of nutrients from breast milk.
Okay.
Okay, and our body is so clever that by 6 months, so if a baby is breastfed exclusively, the lining of the gut by 6 months will be completely sealed and ready to take in solids. And this is why they kind of say that 6 months is pretty much the time that exclusively breastfed baby should be introduced to solids. Now, there's some, I know I spent some time on it, but I think it's important to kind of talk about it, kind of help understanding. There's some evidence, again, very controversial, but very interesting, that babies that are fed by formula, by cow's milk formula, may have higher risk for developing autoimmunity. And the reason for that is because different protein, which are foreign proteins, such as cow's milk protein, can actually infuse through those tight junction as quite leaky tight junction, and then cause autoimmunity through different mechanisms. So this is really, really interesting. I'm sure you agree with me. But I do must say that this hypothesis, again, very controversial, and I think a lot of researchers are trying to kind of prove it, but not completely successfully just yet. But it is very interesting, and it's something we kind of need to know. Okay, let's move on. So we know that the cells are around the gut mucosa. We know that there's the normal epithelial cells, which has those nice little villi to absorb nutrients. But we also have goblet cells. And goblet cells are very important because they secrete mucus. And mucus is very important because it's the primary barrier that limits the contact between the microbiota and the host tissue. And it prevents microbial translocation. So it's kind of like a barrier that kind of prevents movement across the epithelial lining. What's also very important in the mucus is that it gives rise to, or it doesn't give rise, but it's kind of providing a nice housing for the IgA antibodies. So the mucus has kind of two nice little layers, and the innermost is very dense and it contains very few microbiota. And as we go up outermost towards the lumen, it kind of becomes a bit more watery. Microbiota actually have a very nice synergistic relationship with the mucus, because it can actually increase mucus production as well. And it needs it to live within as well. So there's kind of a nice coexisting between the mucus and the microbiota. And this mucus is, I just said that, so basically there's an interplay between the gut microbiota and the mucus. And pathogenic bacteria, pathogenic microbiota, or dysbiosis, can actually lead to mucus degradation and breaking down of this mucus layer. So it's less sticky and it's less beneficial, and the barrier is less effective as well. So these are the goblet cells. You need to know that. And then we've got another type of cells, and these are the M cells. And the M cells are different types of cells. They don't have villi on them, so they cannot absorb nutrients. What they can do, they can endocyte an antigen and transport it into the underlying tissue. And the underlying tissue is loaded with different immune tissue and immune cells. I'm going to have a look at it in a minute. We also have Paneth cells, and those Paneth cells will produce alpha defensin, and lysozyme. And in addition, we also have enteroendocrine cells, which has plenty of T-like receptors and OD-like receptors, and they can stimulate the release of pro-inflammatory cytokines in response to binding to pathogenic microbes. I just want to look at it on a diagram just to show you. This is our mucosa layer. You can see here there's only one layer. It's a monolayer. There's just one layer thickness, so it's very delicate. Okay, the little in between the little cell, we've got the tight junction protein. Remember, they are regulated by what's regulated in the open and the closing of those tight junction?
Zonulin.
Zonulin. Right. So those little epithelial cells, they have villi, okay, so they absorb nutrients. But every now and then we see an M cell. See, the M cell doesn't have the villi on it, but it has a door. It has kind of a magic door. It opens and can endocyte an antigen and bring it down into cluster of immune tissue. Just under the surface, it's called the pair patches. We also have goblet cells here, and those goblet cells will produce
mucus.
And if you can see here, very close to the lumen, the mucus is nice and sticky, and it's full of different antibodies, and it's full of microbiota. And the microbiota, if it's a healthy microbiota, it will induce, it will help the mucus to kind of regenerate itself. If it's a dysbiotic flora, it may break down this mucus, make it more watery and less effective. The different cells that we cannot see here are the Paneth cells. And do you remember what the Paneth cell will secrete?
Is it the defensins or
Yeah,
lysozyme?
yeah. So on different antimicrobial. So this is our layers, okay? This is the epithelial layer. We're going to go back into this diagram a few more times today because I like it very much. So what we also have there inside the lumen, just between the inside of the outside of our environment, is commensal microbiota. And the commensal microbiota is a very generic term of the collection of bacteria that's involved with us, and that it's just there and it's fine to have it there. And it can also maintain homeostasis by directly inhibiting the growth of pathogenic bacteria. And it can do it by one of the following means, okay? So commensal microbiota can inhibit the growth of pathogenic bacteria by competition for nutrients. So basically, it will eat all their food, okay? And you can imagine if there's kind of a nice layer of microbiota, it'll be very good in eating all the food. It will produce short-chain fatty acids. This is important, very important step, because those short-chain fatty acids can have plenty of different roles, okay? So one of them can be, for example, limit the production of pathogenic factors. And we're gonna look at it more later, but short-chain fatty acid, it's a key role of the microbiota. It will produce lactic acid, which will reduce the pH of the environment. And it will produce antimicrobial peptides that will directly affect pathogen growth, okay? So this is the very important role of the commensal microbiota. A very key role is the production of short-chain fatty acids, and we're going to see why in a second. Okay, this slide is important, okay? It's important for the assessment, and it's important in general. So gut microbiota can impact on the intestinal barrier in a number of ways. So it can keep the intestinal barrier healthy and intact and reduce risk for permeability in a number of different ways. So butyrate production. Butyrate is one of the 3 most common short-chain fatty acids. So gut microbiota will give rise to these short-chain fatty acids. And butyrate is a fuel for the colonocytes, for this layer of the epithelial tissue. So in order to regenerate and to keep nice and intact, those colonocytes, those epithelial cells, needs plenty of butyrate. And butyrate is a direct result of fermentation of gut microbiota. Gut microbiota, we already talked about it just a second ago, will produce mucus. A healthy microbiota will produce plenty of healthy mucus, or will help stimulating the production of mucus. And pathogenic microbiota can actually degrade the mucus and make it less efficient for, less welcoming for antibodies, and be more watery and less effective as a barrier. And then another very important and interesting role of the gut microbiota is regulation of genes involved in the maintenance of cell-to-cell junctions, okay? And commensal and probiotic bacteria lead to an increase in tight junction protein. And remember why those tight junction proteins are so important, yeah? Everybody remember that? Yeah. They'll prevent increased permeability. Now, guys, this slide is really important. So does anyone have any question about what we just talked here?
What do you mean by regulation of genes involved in maintenance of cell-to-cell junctions? What does that mean?
It means that it can give, or it can increase production. Basically, those genes will really kind of will lead to a production, or will give order to produce different protein. Okay, there'll be genes transcription, but the microbiota can actually not talk to these genes, but because it's too simplified, but they can regulate their activity. They can regulate messenger RNA to transcribe into cell-to-cell to give rise to cell junction proteins. Okay.
All right.
Is that okay?
Yeah, I think so. Yeah.
Okay. So, any other questions here? Okay. Guys, this is an important, I know I already said it, but this is an important slide, and this is why it's in bold. So, just as we said, we just looked at here, under the layer of this epithelial monolayer, there is the pair patches. The pair patches here, they're kind of collection of lymphoid tissue. And they are, and underneath them, or just within there, it's the lamina propria. I think you should know that from Unit 4. Under the lamina propria, we've got the mesenteric lymph nodes, and then it's the systemic circulation. But this is just what happened just under the lumen, or just inside our, just kind of in between the inside and the outside environment. So they also call the gut-associated lymphoid tissue, and it contains a large number of cells that support the digestive system's function in ensuring that the immune system's response to an antigen is appropriate. And when we say appropriate, it's either inflammatory or anti-inflammatory. So the gut lymphoid associated tissue, which by the way is the largest collection of immune cells in the body, is died within the gut. It's distributed in 3 basic populations. The intraepithelial lymphocytes, and these are the lymphocytes that are kind of positioned in between the epithelial cells. Then we've got the pair patches, which are just right under the mucosa of the small intestine. Underneath is the lamina propria, and then this is a connective tissue. I think you already covered that in Unit 4, but this has also plenty of dendritic cells, macrophages, effector T cells, and those effector T cells will give rise to different T helper cells, and there's also some IgA secreting B cells in there. And underneath all that, we got the mesenteric lymph nodes. So this is just here if you want to look in the diagram. I've got that, just looked at it before. So this is the monolayer, the epithelium. In between here, we've got plenty of immune cells in between. You cannot really see it very well in the diagram. It doesn't show it very well, but there's plenty of kind of cells around here, but also the pair patches. So the pair patches are clusters of immune cells just under the surface of the mucosa. Underneath that, we've got the lamina propria, then the mesenteric lymph nodes, and in the mesenteric lymph nodes, again, there's a big collection of immune cells such as macrophages and dendritic cells and different T cells and IgAs. And from there, it's all drained into the systemic circulation. Now, let's have a look at immune homeostasis, okay? The microbiota evolved at the same time as our intestine. It's there since we were born. Really, we were first introduced to bacteria on our birth canal. So they kind of evolved together with our immune system. Our immune system kind of learned to recognize it as a friend from our very early beginning. So the fact that our immune system recognized the microbiota, because the microbiotic are really, we're just the host to the microbiota, right? It's not really part of us, even though it is, but it really isn't. It's a foreign. It's not foreign. It's there. It resides there, but it doesn't. It's not part of us as per se. But a key feature of the intestinal antigen-presenting cells is their ability to protect the body against infection while still maintaining immune tolerance to normal gut microbiota. So that's just what we said before. So the normal non-pathogenic gut microbiota is those 99.9 passengers that go through Dublin Airport every day. Those pathogenic ones are those 0.0 whatever. It goes there every now and then, but needs to be detected. It needs to be stopped before they're causing damage. Okay. So our immune system, just there, this immune system, it knows that most of the passengers, most of the kind of food particles and microbiota it's being introduced to is friendly. So it's mainly tolerogenic, means it's mainly anti-inflammatory. But when it meets a pathogenic bacteria or a pathogenic or any other type of antigen that it's harmful, it needs to know when to produce inflammatory rather than anti-inflammatory process. And this is the key, the ability of our immune system to distinguish between what is friendly and what is not. This is a key function of our immune system. Now, where was I? So for example, the dendritic cells, I think it's really important to take home that in the mucosal immunity, the most case scenario, there'll be an anti-inflammatory response, because most of the food we eat and most of the bacteria we are exposed to is friendly bacteria. The pathogenic ones are the ones that come every now and then will be detected by our huge clusters of immune cells, the bodyguards in our immune system, or in the mesenteric lymph nodes and the Peyer's patches. So for example, dendritic cells of the Peyer's patches produce high level of interleukin 10. Do you remember what is interleukin 10? Is it inflammatory or anti-inflammatory?
Anti-inflammatory.
Yeah, perfect. So the dendritic cells of the mucosa, and by the way, the dendritic cells on the mucosa layer are different than dendritic cells in different types of the body. There's different types of dendritic cells in different organs of the body, in different locations of the bodies. But those types of dendritic cells that are found on our gut mucosa and in the Peyer's patches will secrete, normally will secrete high level of interleukin 1. Means that will stop and reduce any potential inflammatory response. And this will happen when they sense in microbiota in the gut that would in other parts of the body will induce inflammatory response. So they know that in the gut it's fine. It's absolutely fine to have those food particles or this microbiota or different commensal bacteria, and then they'll secrete as a response interleukin 10 and will stop inflammation. So gut macrophages do not produce pro-inflammatory cytokines in response to MAPS, which is microbe-associated molecular patterns. Okay, you don't really need to remember it for microbiota in the gut. So they've learned to tolerate it in the presence of this type of microbes. And this is important. I think this is one of the reasons. So here we talk a lot about bacteria, but it's completely true for food. And this is one of the reasons why they say that when a baby is small, so from around 6 months to a year, when we expose that baby to a variety of different foods, we may then reduce the risk of food sensitivities, because what we do is that we induce tolerance. We teach our body at this very critical and important time of its life that this is fine and this is friendly. And one of the things that we do or one of the newer approach in people with, for example, peanut allergy, is to give them microscopic amount of peanuts and then increase the dose by the day to rebuild tolerance to that protein, that type of protein. Anyone heard about that before? Okay. So microbe sensing, this is one of the things our immune system on the microbe of the mucosal immune system do. So the function of an enormous function of the immune system is there to control our relationship with the microbiota. And signals from the intestinal bacteria are involved in maintaining tissue and immune homeostasis. The combination of epithelial barrier, which is the monolayer of colonocytes, the mucus layer, the IgA, it likes to live within the mucus layer. The dendritic cells would like to kind of send their dendrites up to the lumen and kind of check what's going on there. And the T cells, they're all comprised of the mucosal firewall, which limits the passage and the exposure of gut microbiota to gut-associated lymph tissue and preventing excessive activation of the immune system and consequent pathology. So IgA is specific for commensals. It's produced to help the intestinal dendritic cells that sample the commensals and associate with the epithelium and interact with B cells and T cells in the pair patches to produce IgA specifics for commensal-derived antigens. In simple words, IgA, they like to sit within the mucus, sit there happily, become very friendly with the commensal-derived antigen, and they're there to support dendritic cells, and if needed, to produce reaction. And really, one of the things we want to see in our gut is good level of IgA antibodies. And one of the things that have been shown to reduce the count of IgA is stress. And this is why we hypothesize that stress may lead to dysbiosis and increased permeability. So we already talked about the M cells, and the M cells are the ones that endocytes the endocyte antigens from the lumen into the pair patches. Dendritic cells can also do the same. They do it in different ways. So as you can see, the M cells have the magic door. They open, the endocyte close the door. The dendritic cells send their very skinny arms up to the lumen, take the antigen, bring it down under the surface, and then assess it. Remember that most of the time, the reaction that will take place, it's an anti-inflammatory reaction. But every now and then, when there's a pathogen, then an inflammation will take place. And our dendritic cells and the T lymphocytes and B lymphocytes, we just learned how they can distinguish between a friend or a foe, right? So what type of interleukin the dendritic cells would normally produce in order to reduce inflammation?
10.
Yeah, absolutely. And let's continue here. We also have plenty of toll-like receptors and node-like receptors on the epithelial layer. And they will just help our dendritic cells and macrophages in sensing any kind of pathogenic substance that may be in the lumen. Again, this is the same diagram. I think it's a really good diagram. That's why I keep bringing it up. But let's again have a look in kind of a bigger, let's have a look at a bigger picture. So here we can see M cells, and as you can see here, under the M cells, there will always be a cluster of immune cells ready, just in case, right? In case that there's a pathogen, they'll be ready. There's the M cells. Underneath the M cells, there's the pair patches. There'll be dendritic cells. Dendritic cells will squeeze those arms, sample, taste the antigen, taste the content of what's happening in the lumen, and then we'll decide should they increase inflammation or reduce inflammation. Most of the time, it will be anti-inflammatory. Every now and then, it will be inflammatory. One of the things that can happen is that if our immune system didn't develop appropriately when we were young, then we won't have tolerance for some of the foods or some of the bacteria that's supposed to be friendly. And then our immune system will react to it. And this is what's called a loss of immune tolerance. Does that make sense, guys?
Mm-hmm.
Yeah.
Yeah. Excellent. So the establishment of tolerance is defined as the active suppression of inflammatory responses to food and other orally ingested antigens. It could not be induced in the absence of gut flora-derived signals, just the one that we've just looked at now. And tolerance is likely to be achieved by different of mechanisms, and you're going to kind of know, you are expected to briefly know those mechanisms in order to complete the assessment. So we know that we have interleukin-10, and we also know that there's different cytokines that will reduce inflammation. And over the past few years, FOXP3 regulatory T cells have taken central stage in our understanding of this process. And what you need to know is, I'm going to look at it in a second. So this is really the process of how oral tolerance is being maintained or created. So those naive T cells will then they can get differentiated into FOXP3 plus T regulatory cells in the thymus, and oral antigens are then sensed by the gut resident dendritic cells in response to dendritic cells producing such a cytokine TGF-beta and retinoic acid, which activate T regulatory cells in the gut and the lymphoid tissue. Sorry, I know it's really sounds really complicated. So when the antigens that are detected by the dendritic cells, recognized as anti-inflammatory or as non-harmful, then the dendritic cells produce different factors, such as TGF-beta and retinoic acid, and retinoic acid is a metabolite of vitamin A. And these two components, or these two factors, will activate T regulatory cells in the gut lymphoid tissue, okay? So dendritic cells capture the antigen. It will produce then factors such as TGF-beta, retinoic acids. These two are anti-inflammatory, important anti-inflammatory factors, and they will give rise to T regulatory cells in the gut lymphoid tissue. And as we know, T regulatory cells will stop inflammation. And this is a very common scenario because, as we said, most of the antigens we meet in our lumen are friendly antigens, come from commensal bacteria and from our food. Any questions on that? It's probably a slide that you're going to need to write a few times to understand, I think. But is there any questions on that? Perfect. So induction of T regulatory cells is proposed as one of the mechanisms of the action of probiotics, and as defined as bacteria known to confer health benefits, okay? So we have some evidence to say that friendly microbiota can actually contribute to
Sorry, there's quite a bit of background noise. Can someone...
Yeah, so someone, yeah. So commensal can also control oral antigen by something. Oh, sorry. So then going back. Sorry, guys, it's late for me too. But those bacteria can also regulate and increase the production of T regulatory cells, and this is how the microbiota can actually contribute to maintenance of oral tolerance, which is very interesting. And the commensal can also control oral antigen sampling by mucosal dendritic cells, and this promotes induction of gut resident macrophages associated with local multiplication of T regulatory cells. They will also limit Th17. That, if you remember, Th17 is a highly inflammatory type of T helper cells, and the response via the production of interleukin-10. So what we need to take home from here, dendritic cells will together with TGF-beta and retinoic acid, will give rise to T regulatory cells. T regulatory cell will block inflammation. Also, the microbiota can directly give rise to some T regulatory cells, will then decrease inflammation. So we have some evidence to say that the microbiota can actually work straight on the T regulatory cells or increase the production of T regulatory cells, same as the dendritic cells. The dendritic cells will do it through the expression of TGF-beta and retinoic acid. If the dendritic cells sense pathogenic bacteria, it won't express TGF-beta or retinoic acid. It will give rise to different cytokines such as interleukin-6, and to then increase the expression of Th17. Okay, this is important. So one role of the short-chain fatty acid in controlling lymphocyte function is only recently been appreciated, in particularly butyrate. And butyrate, remember what we said about butyrate, it's a very important fuel for the colonocytes. But it also appears to regulate the size and the function of the regulatory T cells network by promoting the induction of T regulatory cells in the colonic environment. So butyrate here is a key player in that, together with the commensals. Now, guys, this is an important slide, okay? So oral antigens, so those are the antigens that comes from our food or from our commensal bacteria. They'll be captured and they'll be phagocytosed by gut-resident dendritic cells, okay? They can also be transported in through M cells, but even if they will be transported in through M cells, they'll still be captured under the surface by the dendritic cells in the player patches. The dendritic cells will then move to the lymphoid tissue, where they produce factors such as TGF-beta and retinoic acid. Those are anti-inflammatory factors, and they present the antigen to the T cell. And in the presence of these factors, the naive T cells will then differentiate it into antigen-specific induced regulatory T cells, which will stop and dampen down any inappropriate inflammatory response. So these slides go through what happened in cases of immune homeostasis. This is the healthy, or not the healthy, this is what happened most of the time when the antigen is a friendly antigen. But these slides shows us what happened when the antigen is actually a pathogenic antigen. So if it's a pathogenic antigen, the microbiota will trigger specific toll-like receptor 5 signaling pathway. Dendritic cells produce cytokines which are different. They'll induce Th1 and Th17, and this will secrete different inflammatory cytokines and promote inflammation. Dendritic cells can also promote the secretion of IgA antibodies and producing retinoic acid and B cell activating factors. You don't really need to remember that. What you need to remember is that this is the scenario in most cases, in healthy cases, when the antigen is a friendly antigen. And this is what happened when the antigen is a pathogenic antigen. And all this is thanks to those dendritic cells that found in huge amount in the mucosal layer. And as we know, the dendritic cells, they are not specific, but what they can do is they can digest the antigen and present it into the T cells, and those T cells can then take a more specialized response. Any questions here? I know it's not very easy, especially not at this time of the evening, but is there any kind of particular question I can answer on?
That's fine.
Excellent. Okay. So this diagram shows us what happened in cases of friendly antigen and non-friendly antigens. This side, left side of the diagram, is the kind of healthy, or the when things are kind of happening according to plan. Here is when there's a pathogenic environment. So as you can see here, this cell is a dendritic cell, right? Taste, very lovely and friendly antigen. What happened next? What will it produce? Factors such as TGF-beta and retinoic acid. And retinoic acid, do you remember what's the origin of retinoic acid? Where it comes from?
Vitamin A.
Yeah, excellent. Yeah. It produces these two factors, which will then give rise to different anti-inflammatory cytokines. The most prominent, most common and most important is interleukin-10. interleukin-10 will give rise to T regulatory cells while blocking the production and the differentiation of Th1 and Th17. Is that okay?
Yeah.
Mm-hmm.
On the other hand, you can see here this green and nasty pathogens or pathogenic antigens will be, when they are engulfed and tasted or sensed by the dendritic cells, so it's phagocyted, takes some information in. We don't really know what's the information in, but according to the pathogen, will release inflammatory cytokines. Those inflammatory cytokines will give rise to, so it will block T regulatory cells, but will give rise to the differentiation of T helper cells to Th1 or Th17, depending on the pathogen. It can be both as well. And then what happened? What's the result of this?
Inflammation.
And can you imagine what happened if there's a lot of pathogenic particles, or if there's a lot of different foods that our body does not recognize, that has no oral tolerance for it? What can happen then?
Chronic inflammation.
Chronic inflammation, exactly. And then what happened?
Autoimmune disease.
Then maybe autoimmunity, and then maybe increased permeability probably first, and then many different things that you're going to learn on in different parts of the course. This is interesting, isn't it? Yeah. So going back to a really good question I had on the forum today, and there was a question about gluten, and should we all avoid gluten, because some people say that gluten is inflammatory. Now, after doing this unit, I want you all to kind of understand that gluten is, unless you have celiac disease or unless you have non-celiac gluten sensitivity, your body shouldn't, technically, as far as we know, it's not supposed to react to gluten or protein within gluten, such as gliadin, unless you've got these two conditions, okay? So why does, we're always being told that consumption or high consumption of gluten can increase inflammation? So I think this hypothesis comes from the fact that gluten can interfere with zonulin, and zonulin can or a deactivated of zonulin can then increase permeability or potentially increase permeability. But I think what's this question, why it was so important, is that us as nutritional therapists, we should always aim to really understand the underlying mechanisms of imbalances. And while in this unit we're not really talking about imbalances, we're talking on immune balance. We really have to know how things work in a healthy state in order to understand the imbalances as well. But I think it's really important when we get to kind of, when you progress with the course, is that when you're going to hear a lot of assumptions, and some of them are, all of them have some kind of roots, that they don't just been thrown into the air. But we as nutritional therapists, we want to kind of deep dig and understand what are the mechanisms behind those assumptions in order to make our own critical understanding or critical analysis of what we're being told. Does that make sense?
So, for example, sorry, something like you often hear you shouldn't have gluten if you have an underactive thyroid.
Yeah, but this is to do with antibodies, that they can stimulate antibodies.
Okay.
Yeah, so yeah, what I said now, it was completely generic, yeah, and it was just an example. But what I'm trying to say is that when you hear things that nobody should eat, that should kind of light a red, that should be a red light, and you should say, okay, maybe it's true, because really no one should be really eating like any processed food, for example. But we should know the mechanism behind different assumptions. And it's good, it's important for us as nutritional therapists to understand those different pathophysiological mechanisms or mechanisms that cause to a disease, because then it's easier for us to communicate it to the client. We know what we are doing to the deepest level. It's really hard, of course. It takes a lot of experience and work, but I hope you understand where I'm coming from. So what we are doing in this unit, so by going through oral tolerance, and I'm telling you what happened in this case and how the oral tolerance can be maintained or be disrupted, and you can have kind of a general understanding which will then help you in assessing more complex cases. And this is just balance. So you're going to learn so much more in Unit 7 when you look at immune imbalances.
Okay, so if you don't have an intolerance to gluten, the left-hand side is what would happen. If you have an intolerance to gluten, then the inflammatory response will be. Is that what
Absolutely. Now, I haven't said that it's fine for everyone to eat high level of gluten, because we know that gluten can hypothetically interfere with zonulin. Yeah. And if it interferes with zonulin, then it can increase gut permeability, and if gut permeability is increased, then it can lead to chronic inflammation. But what I did say is that it's wrong to say that what I'm trying to say, sorry, it's so late in the evening, but what I'm trying to say is that yes, it can increase inflammation, but not because all of us are sensitive to gluten. It's because of different mechanisms. In this case, potential increased permeability. I don't think we have enough evidence to state it as a fact, but we have some evidence to say that it may increase permeability through the dysregulation of zonulin. Is that okay?
Yeah.
Excellent. Yeah. Okay. So there's lovely essential reading that you should all include. It's essential, so you should really all be reading it. I'm going to share a couple of nice papers tomorrow about mechanism of oral tolerance, and I'm going to highlight for you the easy parts and the parts that you're expected to understand. So you can use it if you want to kind of be really good in the assessment, and kind of use different research papers. You are more than welcome to use them as well. There's a couple of slides here about diet and the immune homeostasis. They're very straightforward. I'm not going to go through them if that's okay, because it's 9:20 and I wanted to spend 5 minutes on the question of the assignment. Is that okay?
Mm-hmm.
Perfect. But I trust you that you'll get back to me if you've got any questions, and you won't be really quiet. So just very quickly, I know guys, it's really late. Let's have a look at the assessment questions, and if you have queries, just stop me. So Unit 5, we've got a Q&A. So we've got two short question answers, and then we've got an activity. Short question answers, I think I kind of emphasized it today. So list 2 mechanisms by which the gut microbiota positively impact on the intestinal barrier integrity. Quite straightforward. Is that okay?
Mm-hmm.
Should we chat on that, or that's fine, right? It's really just out there in the slide. And then this is a little bit more complex. Explain how the commensal bacteria, vitamin A and vitamin D, which we haven't really covered enough today, but it's just there on the slides, work to maintain oral tolerance. Actually, this year you have to explain how the commensal bacteria with the dendritic cells, because it's really, I forgot to add it here, but it will be in the question. It just makes more sense. So how the commensal bacteria with the dendritic cells, vitamin A and vitamin D, work together to maintain oral tolerance. Again, this is kind of, it's not as easy to write down on a piece of paper, I suppose, but it's all the information is there for you on the slides. And if you need to discuss it more, then you send me a question on the forum. Any question, any queries about that?
No, that's fine.
Perfect. Now, second part of the assignment is a really nice and interesting activity. So what you need to do in this activity is you need to run 2 separate Google searches. In the first Google search, you write intestinal permeability and microbiota. And then you see what kind of resources are coming. You pick one of them. Then you do another research or another Google search. And in the second Google search, you just type in leaky gut and microbiota. And then again, you see what sources are Google gives you, and you pick one. So you can pick either academic or non-academic. You can pick 2 academics or 2 non-academics. But what you can see from the terminology, so what you think gonna happen, where will you get more academic papers? In what search combination? Intestinal permeability and microbiota, or leaky gut and microbiota?
Intestinal permeability is going to be the more scholarly articles. Yeah?
Absolutely, absolutely. So this is your chance to, you don't have to pick an academic resource, but it could be interesting to pick an academic resource and to challenge yourself. The second search would be leaky gut and microbiota, and this will lead you to different type of resources. You pick one of each, and then you're going to have to answer different type of questions, and you need to answer every single question. So you need to describe your findings. So just briefly kind of talks through what kind of you find on each Google search. And then you're going to evaluate each resource that you pick, considering the following points. So you need to cite the resource, and I'm sure you all know how to cite now. There's a lovely guidelines on Moodle. So you're citing it using Harvard referencing system. You need to tell us who published the information. Was it an article, a website, a blog? Just give very clear and succinct details. This is the most important questions out of all the questions. So if you can just expand on that a little bit. Does the information appear valid to you? And give your rationale, and this is important. And why is it valid, or why is it not valid? And what is your rationale for this? So this is the most important question, because this question will demonstrate critical thinking, okay? So what was the author's intention? To inform, educate, sell a product, etc. And does the material or the source reflect the most up-to-date research? And this is the research that's published within the last 5 years. And what topics are covered, and are they relevant to the title of the article or your topic or your question? So it's just really a nice article, giving you the kind of opportunity to look at different resources and be able to kind of critically analyze their validity. And again, this question here, does the information appear valid to you, and give you rationale for this? This is really when you have the opportunity to shine, okay? So this is really when you can demonstrate your ability to critical thinking and think, kind of make your own opinion about different resources. And this is actually, now when I'm thinking about it now, this is really important in the context of what we said earlier about the gluten and the inflammation, and how people may use this terminology not completely inappropriately, but without backing themselves up properly. And then finally, just a little reflection at the end. What could you do to support yourself to develop further confidence in the search and evaluation process? So this is a little reflection, and you need to add a little action plan with that. And when you do a reflection piece, you can do it you can do a genuine reflection piece. Means that you can really sit down and think, how could you support yourself to develop further confidence, or you can just throw in a few lines. If you actually think of it and you actually reflect on that process genuinely and deeply, this will really support your learning process. It will really support you both as a student and as a future practitioner, or as a health coach. You're already a health coach. And I can say on myself that in my own private practice and as a lecturer, I always reflect on what I've done and think in myself, what can I have done better to improve? So this is something that you can actually not just throw in 2 or 3 lines just to kind of get it out of the way, but actually think of it deeply and make the most of it, because reflection is important for further development. And that's it. Any questions, anyone? Okay, I think everybody had enough, right?
Yeah.
Okay. I'm sorry I kept you for so late. I felt like we haven't done enough at all. I would love to see you again. I don't know if you want. If you want to meet me again on Thursday, I can ask more. I feel if you would allow this, just give me some kind of comments on the forum, okay? And if you want to do a little kind of Q&As for the assessment, or if you have any Q&A on the material, we can do it on Thursday. Otherwise, just you can go as wild as you want in the forum. I'll be answering questions every day, or as soon as they come in. Is that okay?
Yeah.
Thank you.
Thanks a million.
Excellent, guys.
Thanks.
Thank you.
Good night.
That's great.
Good night.